To get us started, let me make some introductions. There we go. So first of all, my name is Pete Davey. I'll be setting the scene before handing over to today's presenters. First, let me give a warm welcome and a warm introduction to our guest, Wouter Fellens from Sofics. We are very proud that Sofics has been a customer of EDA Solutions for many years, and during that time, we've seen their reputation grow globally. Today, they're a renowned technology expert in chip ESD protection and a go-to provider for semiconductor IP for high-performing interfaces, PHYs and IOs. Wouter is a senior engineer at Sofics and a graduate of Ghent University. Good afternoon and welcome, Wouter.
Thank you. Good afternoon, everyone.
Perfect. And of course, to my colleague Khalid, welcome to you too. So Khalid is EDA Solutions Technical Manager, and he's responsible for both the pre and post-sales technical team. He's a specialist for analog, mixed signal, and digital IC EDA solutions. Now, today's webinar is going to cover solutions from Siemens EDA for IC design. Before we do a deep dive into the insights in designing overvoltage tolerant general purpose IO circuits within advanced CMOS technologies, including FinFET and gate-all-around architectures. Today's webinar is going to be recorded and it'll be available on demand probably by Monday next week, and that'll be available for you to review and to share with your colleagues. Your microphones are muted for the duration of this webinar, but please use the chat window on the right-hand side to ask any questions, and they will be put to the presenters during the traditional Q&A session, the question and answer session at the end of today's presentation. For best results, best viewing experience, I'd recommend you setting your webinar window to full screen, and you can do that by clicking on the icon in the top right-hand corner, the one which has got the double-ended arrow. So if this is your first time with EDA Solutions, let me say a few words about our company. We specialize in custom IC design and test software, and we're a distribution partner for Siemens. And so, we're a distribution partner for Siemens EDA, and we work with customers around Europe. Now, I hear somebody saying, what does a distribution partner mean? Well, very simply, we sell and we provide comprehensive technical support for products from Siemens for their custom IC, for their MEMS and their photonic IC EDA tools. We also provide a range of expert services, including design consultancy and EDA infrastructure management, both on customer sites and in the cloud. We're based in the UK, on the south coast, close to Southampton, and we have representatives in Grenoble and in Munich. So with the introductions complete, I'd like to invite Khalid to take the stage and jump into today's topic, ensuring reliability in advanced IC design. We're going to be exploring overvoltage protection and verification, and he's going to set the scene of the IC design solutions. So I think myself and Wouter will leave the stage for the moment, and we'll hand over to you, Khalid, and at the end of Khalid's presentation, he'll invite you on stage, Wouter. Thank you very much. Off you go, Khalid.
Yeah, thank you very much, Pete, for the nice introduction. So just an intro about myself. My name is Calibre PERC. I'm the Technical Support Manager at EDA Solutions. And today I'm going to be giving you an overview of the ecosystem for IC design that is offered by Siemens EDA. So to start off, Siemens doesn't just offer you, a set of tools to complete your IC design. It offers you a solution-based ecosystem, a complete solution that answers your requirements for IC design from creation to manufacturing. So on the left-hand side, and for custom IC design, Siemens provides you with robust tools for schematic, layout, and your design library management. And this is done via the custom IC design flow. Siemens' custom IC verification underneath is spanning along the flows of analog, digital, and physical verification. It ensures flawless functionality and compliance, and it includes industry-leading tools such as the AI-powered Solido design solutions, including the Solido simulation suite, Solido design environment, and the Solido characterization suite. The physical verification aspect is done with the very well-known Calibre design solutions. On the right-hand side, the digital design creation and test solution streamlines synthesis and place en route using Aprisa. Power analysis is done using PowerPro and mPower tools. DFT design and yield improvement and safety checks, they leverage the solutions from the test and product line. Digital verification is accommodated by Questa, Veloce, which both guarantee performance. Finally, and most importantly, foundry enablement. We have a dedicated team within Siemens who ensures a smooth trade-off with certified flows from major foundries. And that's, again, driven by a dedicated team. And they ensure that you have access to any process in mind. This holistic ecosystem addresses all challenges, and it makes Siemens the golden standard in semiconductor design and verification. What you have on display is a typical design flow. And as you can see, Siemens strives to deliver a complete IC design to sign-off solution that supports analog on top, digital on top, and mixed signal flows. It integrates, it's an integrated platform that spans the entire IC development lifecycle and enabling efficient, accurate, and scalable design and verification across diverse technologies. The flow is qualified for both FinFET and planar technologies down to 3 nanometer. On the analog design side of things, the flow begins with S-Edit, which is part of the custom IC package, while on the digital development side of things, we leverage the HDL designer tool. Simulation and debug are unified through the Solido design environment, which is offering an AI-powered flow, variation analysis, and advanced waveform processing capabilities using the Solido waveform viewer. The Solido simulation suite takes care of individual analog and digital simulations with tools like FastSpice and Questa, and Symphony provides a robust mixed signal simulation for seamless integration of both analog and digital domains. On the layout design side of things, physical layout of the IC is handled using LEdit. Synthesis and place en route of the digital blocks is handled by Aprisa. And for physical verification, Calibre offers comprehensive DRC, LVS, parasitic extraction, and reliability verification. And it is a fully qualified tool for sign-off at nodes down to 3 nanometer, while also supporting all mainstream and legacy process nodes. Formal verification side of things is performed by OneSpin formal verification, and the TESN DFT solutions provide a robust product lifecycle tools and DFT design side of things in case that you want to introduce design for test features into your block or into your IC. So this solution, this solution-based flow empowers design teams. It focuses on reducing risk, increasing productivity, and ensuring silicon success with precision, performance, and industry-trusted tools at every single stage. So on display, we have many logos of foundries that are supported on our flow, so on our design tools. Our foundry team is more than happy to accommodate, for any additional foundries that are not on this list. This is just an example of the foundries that we support. What we would like to emphasize in our flow is the access to Calibre. Calibre is the golden standard in physical verification for semiconductor design. And with our flow, you will have seamless access to Calibre. Trusted, it's a tool that is trusted across the industry for security and reliability. And Calibre will meet your physical verification and reliability verification needs with unmatched precision. It will ensure compliance with the strictest design and manufacturing rules, fully qualified for cutting-edge edge nodes like 3 nanometer and 2 nanometer processes. It will deliver exceptional scalability and performance, and it's used by top foundries and design houses, and it's the definitive tool for sign-off, making it essential in the verification of today's advanced ICs. For the topic of ESD protection, designing an effective ESD protection is a balancing act. Too little and the circuit is at risk, and too much, the performance and the area might suffer. So especially in high-speed or RF applications, traditionally ESD design is either limited to small IP blocks or relies heavily on manual effort. And this can miss critical system-level issues. The figure on display shows legacy verification, and it relies on manual partitioning of small block simulations. And this makes it hard to account for real parasitics and dynamic behavior across the full design. And this approach doesn't scale and often leads to unreliable and unpredictable results. Introducing Siemens's solution to this problem. And to solve this problem, Siemens has combined Calibre PERC's reliability rule checking with Solido simulation suite AI accelerated spice analysis. With this integration, it will allow for an automated context-aware simulation of ESD networks across the full chip. PERC would intelligently identify relevant protection structures, and Solido runs detailed simulations to detect weak points and validate design margins. This approach gives designers a scalable, accurate way to ensure robust ESD protection without compromising performance and without needing to over-design. It streamlines the process and increases confidence in tape-out reliability. One of the key use cases for this technology is verifying whether devices are at risk of breakdown during an ESD event if certain discharge paths do not meet the foundry-specified resistance criteria. The context-aware flow automatically identifies failing paths and launches simulations to determine if these paths pose a risk to the devices. And then engineers can then decide whether to request waivers from the foundry or make necessary design adjustments based on the simulation results. With the Siemens custom IC design flow, design faster, verify smarter, and deliver with confidence. And with that, I hope I have given you a comprehensive overview of our IC design ecosystem and touched on some of the key issues in ESD design. I now would like to hand over to Walter from Sofics, who will talk about the design of overvoltage GPIO using the Siemens EDA tools. Walter, over to you.
Thank you, Khalid. So my name is Wouter Valens. I am a senior engineer at Sofics, which is an IP company working on processes all the way from BCD technologies down to regular CMOS, FinFET, all the way down to 2 nanometer gate all around. We're a company mainly focused on the chip edge, so everything interacting from the core to the outside world, be it analog IOs or other functional IO circuitry mainly. Today's talk, I'm mainly going to focus on the design of an overvoltage tolerant general purpose IO, where we use the Siemens EDA tools to do this whole design. First, I'm going to explain a bit on what is an overvoltage tolerant IO. Then I am going to continue with how we do the design. Next on, I am going to discuss the layout steps with a particular focus on the FinFET nodes. And lastly, I'm shortly going to touch on the verification of all these things of the design. So, overvoltage tolerant GPIO. First, let's explain what is a GPIO, what is overvoltage tolerance, and why do we need it? And lastly, what are the design challenges, which, spoiler, they are mainly SOA issues. General purpose I/O is an I/O typically working at a speed in megahertz terms, be it 1, 10, 100 megahertz, which basically puts bits from the core onto a bus. Typically, this GPIO consists of several building blocks, a driver, which will be the main focus of this talk, which puts a bit safely onto the bus. The receiver does the inverse. It reads the status of the bus and translates this to a bit towards the core side. Also, there is very often a pull, which if there is no driver setting the path voltage or the bus voltage, which sets then the pull, pulls it high or low to a supply rail. And lastly, there is ESD protection because this path is connected to the outside world, and we need some ESD protection for robustness. So how does this driver look? Typically, it is consisting of two big MOSFETs connected to the path, which we call the driver, and then the pre-driver, which is basically a buffer so the core signal can be put on the gate of these MOSFETs to control them correctly. Now, that is a general purpose I/O. Let's talk about an overvoltage tolerant I/O. What is it? It is an I/O where the voltage, the supply voltage is higher than the maximum allowed voltage on the separate devices. So on the different MOSFETs inside of the design. For example, in 7 nanometer FinFET technologies, the I/O devices can handle 1.8 volt. But what happens if this 7 nanometer chip wants to talk to a 65 nanometer chip, for example, which uses 3.3 volt I/O voltage? Either you don't, or you make an overvoltage tolerant I/O, which in this 7 nanometer technology still makes use of a 3.3 volt I/O voltage. I'm going to talk about it with a very specific design example. So let's say the VIO is 3.3 volts and our maximum allowed voltage is 1.8 volt, or maximum allowed voltage over one device, that is. Let's have a look at the issues. The first thing that breaks is the pre-driver. These typically consist of inverters. So if you put an inverter way too high of a voltage on top of the inverter, the MOSFET inside of it breaks. So how can we fix it? We limit the amount of voltage over the pre-driver. And we do this by introducing an extra voltage domain, the VM or middle voltage. Why middle? Because this is typically in the middle of the VIO and VSS rails. In our design example, this would be 1.65 volts. This way, we can run the PMOS pre-driver on a domain between VIO and VM, which limits the amount of voltage seen by the pre-driver. And similarly, the NMOS pre-driver we can run on a VM to VSS domain. Of course, these are different domains than the core voltage or the I/O voltage, so we will need a level shifter to go from one voltage domain to another. Okay, we fixed the pre-driver. Is there something else that breaks? Yes, the output MOSFETs also see this 3.3 volt output swing. So could have that between their drain and source terminals, this full 3.3 volt swing is seen, and this would break the device. So the typical way to fix this is by stacking two devices on top of each other. This way, the voltage gets distributed between each of them, and if you look at only one of them, the voltage does not exceed the maximum allowed voltage. Now we have our switching devices at the fully top and bottom, and in between our protection devices. What gate voltage should we connect them to? Well, if we connect them to the already existing middle voltage, VM, we can easily protect the different devices. The downside of this stacking solution is that for a similar drive capability, a similar RON, you need at least 4 times the size, but in practice probably even more. This because you have 2 devices, and each of these devices will need to have the double width because they are in series with each other. So if we now look at what kind of extra design complexities do we have introduced a level shifter, which needs to be designed and also work on this higher over voltage and not break. We have introduced an extra voltage rail so that we will need to generate typically internally on the chip with another bias generator. And the ESD cell connected to the pads also needs to be over voltage tolerant in our design example. So let's have a look at now our stacked driver. Did we actually fix the issue? Well, let's have a look at the NMOS side, for example, when it is in DC operation and it is in high Z mode. Let's say the pad is 1.8 volts and we are working with devices of 0.9 volts. If both of our devices or NMOSes are the same size, they are both off and they will have the same off resistance. This will lead to the middle voltage being nicely the middle between 1.8 volt and 0 volt or 0.9 volts, and we will have no SOA safe operating area violations. Just realized I forgot to explain what a SOA issue actually is. This is a safe operating area violation, means that it leaves the safe operating area of the device, which happens when the voltage over 2 terminals of this device becomes greater than the allowed voltage over these 2 terminals. Okay, so if both the MOS devices in our stack are equal, everything is okay. But what if, for design reasons, we did not choose these the same? For example, if the protection MOS is twice the size as the switching MOS, then if we then doubling the size, the width of the protection MOS halves its off resistance. So this means the middle node will have a different voltage. In this case, it will be 1.2 volts, and this 1.2 volts is bigger than the allowed maximum voltage over the bottom switching device. So we will have a safe operating area violation, which is, of course, not good. So this poses a design constraint that both devices will need to be equal size. There's no time to elaborate on this now, but also in transient, different design trade-offs will pop up, which will limit the choices you will be able to make in these sizings. Sometimes even making it impossible with this architecture. Okay, we have gone over an overvoltage tolerant I/O. What is it, and what are the design challenges? Let's start designing it. Our design process is equal to the one proposed by EDA Solutions, where we follow the analog path. We start by designing our schematics in SEdit, which we then simulate in the AFS simulator. This is of course an iterative process, and yeah, we continue on this process up until the design meets all specifications. Once that the design is done, we continue on to layout in LEdit, where we use, after which we use Calibre to check DRC, LVS, and XRC, which couples in back to the simulation environment. So first off, is SEdit, where we make our schematics, and typically we include the expected layout parasitics already in this step. This is especially important in the overvoltage tolerant case, since a lot of parasitic diodes can play an important role in excessive leakage currents or otherwise major issues. One of the things we extensively make use of is tickle scripting. Since we are an IP company, we work in a lot of different technology nodes. So we have a need to easily port one design from one technology to another. And we use tickle scripting for this. One specific example is seen in the bottom left, where we use some tickle scripts to set the initial variables, initial sizings of all devices inside of our design. Also, we added some custom check and save rules so that we can check our design conventions, which we made in-house, if they are followed or not. Lastly, there are some test benches inside of this design step, where we test for all corners and system modes separately. So all system modes go through all PVD corners, where we vary MOSFETs, resistors, everything independently of each other. The simulation happens with AFS, and we view the results in the waveform viewer of EDA Solutions. The main extra bit on the overvoltage tolerant case is that we check the SOA violations with assert statements. What this is that the simulator flags if anytime a voltage goes over the maximum allowed voltage, or in other words, if we have a SOA violation. After this reporting, we do some extra filtering. This is because, for example, if you have a 1.8 volt device which can handle 2 volts, but that if you combine that with a supply voltage of 1.8 volt plus 10%, also 2 volts, any little bit of noise on top of that will trigger a SOA violation, which in practice will not be an issue. This is one example of the SOA violations which we will filter out. The way that these warnings, the AFS reports this is first indicating what simulation the error occurred in, and then for inside of the simulation reporting every violation. It states the instance name and the pin combination, as well as the value at the end of the simulation, so that the SOA violation fixed itself. and then some more information about the violation itself, such as the time it occurred, so you can find it back in the waveform viewer, the peak value, and the duration of the violation. If, for example, you are making 1 megahertz I/O and the duration is 1 picosecond, it is probably not that severe. But this has to be looked at on a case-by-case basis. One practical, concrete example of such a SOA violation was seen in an AND3 gate. If the A3 and A1 terminals are low, the yellow marked nodes are basically floating. Now, if A2, the middle gate voltage, now switches from a high voltage to a low voltage, this capacitively couples through to the marked yellow voltage nodes, and we have a SOA violation between the VDD and these marked nodes. So this will give an issue. This is just one example of where that we see violations in a very, very standard cell. So if you do this, do take a look at all violations, but don't be surprised in how many you will find. Okay, so we've taken a look at all violations, we fixed them, and we are confident in our design. Let's go on to the layout step. The special thing here is that one I/O contains multiple different layout styles. We have a digital layout style where we mainly make use of the standard cells provided in the PDK. We have an analog/mixed signal layout where it is digital, but it is much more focused on layout parasitics. There is an analog style where matching becomes important, noise becomes important, those kinds of things. And there is an ESD layout style that we use for very where we really make our own custom devices for very, very high performance ESD protection. Sometimes, depending on the speed of the I/O, we also use some high-speed concepts, such as making symmetrical delays between two lines, but this is highly dependent on the speed of the I/O that we are talking about. So let's start with the digital logic. Here we use really the standard cells. This is for stuff like processing the core signals or for handling certain protocols. One example of this is a selection for how much drive strength do we want in our I/O. Typical of this layout style is that we make use of with space patterns. We make heavily use of the PDK standard cells, which very often are already colored in metal. More on this coloring and the verification stage. Also, what I would call digital layout, but more analog minded is or analog mixed signal layout style, where the devices themselves work in a digital fashion, but the layout parasitics matter a lot. For example, in a level shifter, you need symmetry between the two branches. In an output stage of a driver, you have very big currents, so any little extra metal resistance in the current path is very much an issue. So this leads to custom metallization. Deep annualization tubs are also something similar. This is very much more of a custom layout than with space patterning, for example. Then we have the pure analog layout style. This is, for example, in an LDO for our mid-node voltage generation, we use this analog layout style. Or for if we implement a receiver, making use of a differential pair, the matching between these two OTA MOSes is very important, or current mirrors. So then we look way more into matching and noise. This is a craft of its own, let's say. Lastly, we have the ESD layout style, where we actually make our own IP devices. This is really not using the existing PDK devices, but making our own by drawing polygons, by actually drawing the layers directly, which will come onto the silicon. This is a layout first design very often, so we will start by making the layout, including a well thought out strategy on all the layout parasitics, which we will then in a later step translate to schematic. The application is of course ESD protection, and the example given here is the IO voltage, the protection for this IO cell. So we've drawn our layout. Let's check if we did a good job or not with verification. There is the DRC, of course, which includes dummy fill, especially at these more advanced layout nodes. At these more advanced technology nodes, the dummy fill is a really important factor. We have much more strict rules on density, and the dummy patterns themselves become more complex as well. A second thing, interesting thing is the metal coloring, which can happen automatically already in a lot of DRC runs, which is a big help. Just as a ballpark, I think in these more advanced nodes, the DRC manual has been easily times 10, times 20 in size. So the DRC and performant DRC checker is important. Then we have the LVS, where we definitely include the layout parasitics. For example, the well diodes. Again, since we are talking about over voltage tolerant things, incorporating these is very important. We also make our own IP devices. So in order to check them with LVS, we write our own LVS rules, so these get recognized. Of course, after the layout, we need to check if the design still works, and we do this via XRC or parasitic extraction, which feed back to the simulation. And lastly, you can use PERC to check the full chip ESD safety. So in summary, we've talked about overvoltage tolerant IO, where in concept it is just stacking of devices or limiting the voltage over specific devices. But if you look into more detail, there are a whole bunch of SOA violations that need to be addressed. We do the schematic design with S-edit, and we make heavily use of tickle automation. In simulation, we use AFS, where we automatically check all these SOA violations and where we filter them out already somewhat, so we only have a look at the interesting ones. In layout, we make use of multiple different styles of layouts, which are all present. And in verification, we have DRC, LVS specs, and PERC that we run. Sofics is not only a company making overvoltage tolerant IOs. We have a quite extensive ESD portfolio as well, or analog IO. They are very similar in nature, where we focus on higher voltages, higher than the PDK allows, or high speed. In practice, this is very often low cap, 5 femtofarad, 10 femtofarad. Protection cells are definitely possible. Low leakage, similarly, picoamps of leakage is for sure possible, or just simply a higher performance ESD cell, which leads to lower area or higher ESD rating for the same area. Next to this ESD story, we have other IOs available as well, where we focus on higher speed interfaces. 20 gigahertz, 30 gigahertz are just some of the ballpark values, or other things such as bias generators, which have a much lower quiescent current. So yeah, that's it for me. I think I'd like to give the word back to Pete.
Excellent job. Thank you very much, Wouter. Just to remind you, today's session is recorded and it will be made available on demand, and you'll be able to access that from the EDA Solutions website probably by Monday, but we'll drop you all an email so you can review anything or share it with your colleagues. If you specifically would like copies of slides, I'm sure we could arrange that. If you drop us an email, you can see Wouter's and Calle's email at the bottom there. So with that, I think, Calle, thanks for joining us again. I'm just going to dive straight into the question session. We've got a handful of questions which have come through the chat window. If you've got any questions on your mind, please pop them into the chat window now. If questions arise whilst we're answering these ones I've got online, please add another one to it. First question, this one's for you, Khaled. It comes from Stefano in Italy. Does the flow that you talked about support 16 nanometer process from TSMC?
Hi. Yes, we do support FinFET technologies such as the TSMC 16 nanometer. Oh,
that was a nice quick answer. The first few questions are going to be on the first half of the presentation because that's the order they're coming in on the chat window. So next question from Niels in Sweden. Can you tell us a bit about how well the flows actually integrate together, and do I have to own all the tools, Khaled?
The flow itself is quite modular, so you don't have to commit to the entire flow. You can use a schematic editor, for example, and then the simulator alongside it, and then have the layout editor maybe at a later stage, or you can pick and choose. Basically, you don't have to stick to the entire flow. And in terms of integration, it's very tightly integrated, means that each tool can call the other tool using buttons and the interface. You can call the Solido design environment from SEdit. You can call Aprisa from I'll for synthesis and place and route. And so it's overall, you can also back annotate results from the simulator and from Calibre for DRC and LVS violations. So it's tightly integrated.
Thank you. I hope that answers your question, Niels. Next one is also coming from Northern Europe, from Ireland, from Siobhan. Can I read design data from other tools into the Siemens tools?
Absolutely. I mean, the Siemens tools, they support industry standard formats. So if the set tools support open access, for example, that's just an example, then yeah, our tool are natively open access. So you can explore the open access database. You can make changes to it. Similarly, we support Oasis and GDS formats and plenty other formats that are industry standard.
Great, thank you, Khaled. I'm gonna jump around a little bit now and bring Wouter back into the conversation. Question for you from Sebastian in Germany. Are there other safe operating area issues present in the I/O which has not been shown in this presentation?
Yes, absolutely. Especially in transient, there is issues both in the falling edge as well as in the rising edge. I've actually prepared some slides for exactly this question, since it is indeed a very good one. For example, in the falling edge, you have the issue that this mid-node voltage falls way faster than the bad voltage. This is because of two reasons. One, its capacitive, its parasitic capacitive load is way smaller. And secondly, the drive strength of the switching MOS is way bigger because its gate source voltage is bigger. And this could lead to an issue in falling edge. One solution to this could be to increase the size of the upper of the protection MOS. But as I've said earlier, there's also one in the rising edge, which is a bit more tricky to explain. But it's basically that if you turn off the NMOS driver, then the pad voltage starts to rise because of the PMOS driver probably, or because of the pull-up. And at a certain time, this mid-node voltage will become floating. But because of the parasitic capacitance, the source drain parasitic capacitance, the mid-node voltage will rise even more, maybe even higher than the maximum allowed voltage. One solution to this is to increase the bottom device compared to the top device, but that just counteracts the solution I've said before. So if you are in that case, you will need a different architecture, which we have some solutions for. But yeah, that's just two of the possible SOA issues only in the driver.
Cool. Thank you for your question, Sebastian. I hope that answered it. I thought it was a longer answer than I was expecting, but great stuff. Next one, Wouter, you might want to backtrack to slide number 28, because we've got a question from Paul in Romania regarding that slide and something you said with respect to parasitics on the schematic. Do you mean that adding them before running PECs? And if so, how do you decide on which values and devices to use?
Yes, absolutely. Running them before PECs. In order to PECs, you will need some layout, which will mean you are way further down the design flow already. So already including some layout parasitics that you expect very early on in the design process will help a lot. I'm mainly talking then about well diodes that you expect. And there, just adding them is most often already sufficient. Because if these diodes come in forward conduction, then they will already conduct significant current, even if they are quite small. A second good thing to add would be to add some estimation on parasitic capacitances, but these are indeed more tricky to size correctly, and there it is mainly a case of design experience and a best guess effort.
So great, we've Paul's got a follow-up question to that. So regarding the bias circuit, its implementation is more like an LDO or something simpler, like a GM bias generator. And also, usually, is there a bias circuit per pad for multiple pads, or is it global power rail for all pads?
Again, great question. It is An LDO implementation is quite typical, yes, but we are definitely looking into other implementations as well, because one downside, for example, for an LDO implementation is that this is very good in delivering current into one direction, but if there would be some current pumped into this supply rail in the other direction, an LDO is not good at handling this. So absolutely looking into other biasing strategies is a good idea. And very often these bias generators are shared across multiple I/O cells because they are the main consumers of power, actually. This mid-node circuit, mid-node voltage is used to protect the I/Os, so it needs to be always active. So it is important to keep it as low as possible. So if you can share this bias generator across multiple I/Os, that is definitely a plus. And lastly, how this is made, yeah, this could also be made off chip, but then you need an extra pad, and yeah, that includes all the issues with that. But it's all an option, basically.
Everything is possible. So next question, which is related, is from Stefan in Germany. I think you started to touch on this, Wouter, but how much supply current is usually used for the VM voltage generation?
Yeah, I think if we use an LDO type design as a bias generator, we typically aim at around maximum 60 to 100 microamps of steady state current per bias generator, that is, which you can typically share over multiple I/Os. But we are looking into other topologies which are consume in steady state almost no currents. No current being 100 nanoamps, 1 microamp, something in that order of magnitude.
Thank you. Thank you for your question, Stefan. Next question, which just popped up actually from Prince Stefan says thanks, from Prince in India. So thank you for joining from there. It's maybe getting a little bit late, but I'm not sure who best to answer this one. Maybe one
on my side.
So how efficient are tickle scripts when it comes to schematic porting?
Well, the question is, do you need to do porting at all? You know, if you already have open access, you can just open it in our tools, you know, and work with it. But then if you're talking about, say, a format like EDIF, then the tools already do this for you. So you don't really need to do it yourself. Depends on the format you're coming from at the end of the day. But then, you know, if your last resort is that you have to do, you know, porting through Tickle, it's already been done. There's even scripts for this. So it's quite, from how efficient the script is. Well, how efficient the script is? Well, it's easy to use language, and it's also fast, and it's already been done. So yeah, we'd be happy to support with this. Yeah. Maybe Wouter can share his experience.
Yeah, because in my world, let's say, porting means translating from one technology node to another. So which are both open access in that case. And there it is really fast actually to do this via tickle scripting, because Khaled, stop me if I'm saying wrong things, but a lot of the functionality of SEdit is under the hood already implemented with Tickle. So we are just using the same functionality already present.
Yes, Asset already has Tickle API that that handles a lot of the instance manipulation, connectivity and so forth. I noticed also a comment from John about existing PDKs. Indeed, I'm entirely assuming that you have, you would have a PDK that is working with Asset. As I said, we have a dedicated PDK team that is continuously working to enable more and more of those processes in our flow.
Great, thanks, Bill. And next question I'm going to ask, I'm not sure, I think this might be from your boss, Wouter, who's joined us, someone called Bart. So I'm not sure if I'd asked the question or not, but I'll take it at face value. The question is there a lot of difference in layout complexity and tool usage? For example, CMOS nodes at 130 nanometer, FinFET at 4, gate all around at 2.
Yes, absolutely. Regarding tool usage, it is on the technology installation side, let's say, it is very similar. Metal coloring is one example that needs to be installed correctly, but once it is installed, it runs very fluently. But layout complexity really jumps a lot from CMOS to FinFET and from FinFET to gate-all-around. Again, the best indicator for this, for me, would be the size of the design rule manual, which goes times 10 times 20 easily. A 1,000-page document plus isn't very common.
Okay, I've got 2 more questions in my queue. So if any of you out there have got any other questions on your mind, please pop them into the chat window. So I've got this one I'm going to give to you, Khaled, from Maximilian in Austria. We have to have a question like this. It's de rigueur for nowadays. What aspects in the flow use AI?
Well, the Solido design environment uses AI in making your simulations faster. It incorporates machine learning algorithms to speed up the variation type analysis. You can run thousands of simulations in much shorter time compared to brute force SPICE simulation approaches. So that's one of the focuses that we have used AI in Solido design environments.
Okay, thanks. I'm going to make a shameless plug here at this point for Siemens user-to-user conference, which takes place, I think it's on May the 13th in Munich. So it's coming up fairly shortly. I know that the CEO of Siemens EDA, Mike Ello, is giving presentations on the use of AI and digital twins. So it's a very apt topic. Of course, lots of people are talking about it in all sorts of application areas, but I'll pop a URL in the chat window. If you haven't already seen the schedule for user-to-user and you think it might be interesting, then please take a look at it. Whilst I do that, I've got last question for in the queue at the moment for Wouter, and it's from Doron in Israel. Have you got any cool story to mention why Siemens EDA tools are so great?
Maybe last summer we did the 2 nanometer gate-all-around tape out, and actually 2 things about that. We asked we just to compare different vendors. Of course, we asked Cadence for a quote if they could support us with it, and they were unable to give a quote because it was too advanced for them for European customers. So EDA Solutions was the perfect option for us as a European customer. and two, we actually were the only ones who gave in a clean design on tape out date. There was some issue with there was some issue with the other EDA solutions, the other software used, while Siemens or EDA Solutions didn't have that issue, and that was why everyone else had to last minute still scramble and do a lot of last minute effort, while we were able to deliver it on time.
Cool. Well, thank you for that. Actually, that wasn't in the practice run for this webinar, but that's great, and the check is in the post to you. So with that, I've just posted the link to where you can find out more information about user to user. I don't have any more questions. I think what I'm going to do is I'm going to ask our speakers if they'd like to make one or two last comments. So if you do have a question, pop it in the post, and we will ask before we just finally sign off. But Wouter, as our guest presenter, first of all, I'd like to say thank you very much for presenting. Fantastic stuff in there. Any final comments from you?
Thanks for having me. It was a pleasure to present.
Cool. And Khalid,
Yeah.
thank you very much for helping out again with all the detailed technical stuff. Would you like a closing comment from yourself?
If you have a design challenge or you would like to improve your design flow, get in touch. I'm pretty sure we can accommodate. So, yeah. And thanks for tuning in. Yeah, thank you.
Yeah, we'll certainly do our best. So with that, actually, there's one last bit popped in there by one of our guests online saying that watch out for some AI announcements from Siemens at DAC. Of course, that'll be coming up. Or when is it? I think it's the beginning of July. Anyway, not too far away. So any of you out there are lucky enough to be going, that's something to watch for. So with that, thank you again to my presenters. Thank you very much for all the hard work you've done preparing for this. And to all of you out there who've joined us, we appreciate you investing your time here today. I hope it's been valuable. If you've got any questions, don't hesitate to pop a question in. Either remember the email addresses which are on the pages earlier, or I'm sure you can go to sofics.com or edasolutions.com for their contact page and pop a question in there. So with that, thank you very much for joining us today. Hope you found it valuable, and I wish you an enjoyable rest of the day. Thank you and goodbye.